Drozd from Institute of Mathematics, National Academy of Sciences. The title of the talk, Quasikrullian rings and their divisorial categories. Okay.
Is it okay?
I also see myself in this screen. Just a moment. What if? No, it's probably not good.
Yeah. Do you see my screen?
Yes, we see your screen, but you see this little screen at the bottom right.
Oh.
Could you move it somewhere?
Oh, yeah.
Oh.
Okay. Now I think it's okay. Yeah.
Okay.
Okay, thank you. Oh, sorry. What's the matter? Yeah. So my talk is an attempt to consider some rings of models of a commutative rings. So some categories of models of commutative rings, which, or better to say, some quotients of these models. So I will call them divisorial categories. I recall that divisors were introduced by Kronecker as another approach to the arithmetic of algebraic numbers. And this approach was also used by Hermann Weyl in his algebraic theory of numbers. And Kronecker's approach obtained development in algebraic geometry, where it was immensely and fruitfully used. In purely algebraic form, it can be found in Algebra Commutative put by Bubraki in chapter 7. And in particular, one can see there that a natural frames of this theory of divisors and divisorial models is a third quotient of the category of models by those concentrated in dimension greater or equal to. This quotient was studied by Istvan Beck in 1971, who in particular showed that this category for Krull rings or for integrally closed domains is of global homological dimension 1, just as the category of torsion-free models of algebraic numbers. The aim of my study was to extend his consideration to a class of rings that are not necessarily integrally closed or even domains. Now I go to the definitions. A commutative ring A is called pseudo-Noetherian if for any A, this set of minimal prime ideals containing A is finite, and for any prime ideal from this set, the localization is Noetherian. For instance, For instance, it's always so for Noetherian rings, yeah. But this, and also for Krull rings. Okay, then if we take any prime ideal from this set of minimal containing A, its height is at most 1. And if A is non-zero divisor, then this height is equal to 1. I denote by P the set of prime ideals of height 1, and by Q the full ring of fractions of A, that is the ring of fractions with respect to all non-zero divisors. A pseudo-Noetherian ring is called pseudo-Krullian if it is reduced, that is, has no nilpotent elements, and locally defined, that is, it coincides with the set of all elements from full ring of fractions, such that for any prime ideal of height 1, there is an element which is not in this prime ideal, such that R times A is in A. Or if A is a domain, it just means that A equals the intersection of all its localization by prime's ideal of height 1. So it's, for instance, for all 3 domains, in particular for Noetherian integrally closed domains. And from now on, I suppose that A is a pseudo-Krullian ring. I denote by X this full subcategory of A models, consisting of those models which whose localization are 0 for all primes of height 1. It is a Serre subcategory, so the quotient of A models by X is well defined. I denote it by A mod tilde. And moreover, one easily sees that it is a localization subcategory. Namely, it follows as any model contains a maximal submodel, a biggest submodel from X. Yes. I recall that localization means that there is the natural projection of A models to A mod tilde has right adjoint. That means that home tilde of Fm to M equals home from M to Gn. I denote by home tilde the homomorphism in tilde category. I call a model M codivisorial. This is term of Ishbun-Beck. If there are no homomorphism from models from X to M. Or the same, M has no submodels from X. And I could call it closed if both home xm and x1 xm equals 0 for any x of X. So there are no submodels and no extensions, non-trivial extensions of M with these one trivial models. The following facts, I know the closed is the term of Gabriel from category abelian, and the following facts are due to this paper of Gabriel. M is closed, then for any n, homomorphism from M to M are the same as in the category of models and in this quotient category of tilde category. M is closed if and only if M is isomorphic to its closure JFM, or the same, M is isomorphic to Gn for some model N. So it is obtained from some object of the quotient tilde category by its right adjoint G. And moreover, the pair of models F and G, if F restricted to the category of closed models, is an equivalent of the category of closed models with this tilde category. An important example, if A is local Noetherian of call dimension 2, then M is codivisorial if it has no simple submodels, and if it's closed, if and only if it is a maximal Cohen-Macaulay model. Now suppose that A is a torsion-free A model, for instance, an ideal of A. Then it embeds in this rational envelope, the tensor product, this ring of quotient. And I call A divisorial if it coincides with the submodel AP of this envelope, which is which means that for any if an element from this rational envelope is such that for any p there is an element R not from P, which are such that Rx is in A, then X is in A. Why I'll call it divisorial? Now I can explain this term codivisorial. Namely, one can prove that M is codivisorial if and only if the annihilator of any element from M is divisorial. Moreover, if M is codivisorial and there is an essential extension of M, so we embed M in bigger models such that it is essential, which means that any non-zero submodel of M dash has a non-zero intersection with M, then M dash is also codivisorial. It is more or less clear. And on the contrary, if M is embedded in M dash such that M dash is codivisorial and the quotient of M dash by M is in X, then it is an essential embedding. Okay, maybe I will show yes. If N is finitely generated, yeah. Oh, no. For instance, if it is, no. Your pardon, I have done something. Oh, yeah. This is, for instance, if M is codivisorial and E is its injective envelope, so that means that M embeds in E this injective model such that this embedding is essential, then we can construct this GFM as the maximal submodel in A, such that it contains M, and the quotient of Cm by M is in X. Okay. Yes. An important remark is that if we take a prime element, a prime ideal of height 1, then every AP model is, if considered as a model, is closed. Moreover, it has no X with elements from high at all. And the theorem, we can prove the following theorem. If a model is Gaussian, then its closure, its GFM, is isomorphic to the coproduct or direct sum of all its height 1 localization. And if M is torsion-free, then it is closed, if and only if it is divisorial. Now, I'm going to injective models. Namely, I'm going to show that injective objects in this quotient category, in tilde category, behave as injective models over Noetherian rings. An important remark that any codivisorial injective model is automatically closed because it has no X with anything. Yeah. Moreover, if an injective model is J is codivisorial, then its projection or tilde category is also injective, and moreover, all injective models in tilde category are of this kind. It is also proved in this category abelian, but Gabriel. Now we can give a complete description of divisorial injective models and hence of injective objects in the tilde category. Namely, I denote by EM the injective envelope of M. If M is divisorial, so is EM. And I denote by Qj the simple components of the semisimple ring Q. Q is semisimple as A has no nilpotent elements. Namely, Qj is localization of A by a minimal prime ideal. And I recall that there are only finitely many minimal prime ideals because this is just the minimal of 0. Theorem. So I prove the following theorems. First of all, every indecomposable injective codivisorial A module is isomorphic either to this component of Q or to injective envelope of A modular prime ideal of height 1. The second, every coproduct of codivisorial injective models is injective, and every codivisorial injective model is a coproduct of indecomposable. And finally, if all models Mi are codivisorial, then the injective envelope of their coproduct is the same as the coproduct of their injective envelopes. So this is just as was proved by Metlis for injective models of Noetherian rings. So in this sense, yeah. In this sense, this category, yeah, okay. Now, one more important fact. Let M be a divisorial torsion-free module and set MP plus the form from PMP to MP. Namely, we can identify this MP plus with this circle of injective, of divisorial, rational envelope of M, or the same. This is injective. I call this is also injective envelope of M. With the circle of this quotient. And note that this is finitely generated, always, because AP is Noetherian. And moreover, sorry, not finitely generated, but it is the direct sum or coproduct of several copies, maybe infinitely many copies, of AP modulo PAP. And then the corollary is that the injective envelope of the quotient of this rational envelope by M is just a coproduct of injective envelopes of A mod P in some powers, in some. Then we can prove the following thing, that injective dimension of this element Fm in A mod tilde is equals this supremum of injective dimensions of its localization by P from of height 1. And global dimension of this category, tilde category, equals the supreme of global dimensions of localization of A by primes of height 1. Now, in particular, if A is a Crowley ring, for instance, Noetherian and Noetherian integrally closed domain, then a mod tilde is hereditary, that is of global dimension 1. So all x tilde I are 0 if I bigger than 1. One more theorem about torsion models. Suppose that M is torsion and consider its minimal injective resolution. Yeah, so there's such injective resolution that each injective model is an essential extension of the image from the preceding. If we take this direct sum of all these injective resolutions of models FP and project it to tilde category, then it is a minimal injective resolution of FM in tilde category. And if n is finitely generated, then tilde x, that means the x in the tilde category of n with m, is equals the coproduct of xi of localizations. It implies the following thing. If A is a Krull ring, for instance, integrally closed Noetherian domain, then if we take its tilde image, its image into the category, then it is direct sum of torsion part and torsion free part. Just, I recall that for integrally closed Noetherian domains, it is proved in Algebra Commutative Bourbaki in chapter 7. So it follows immediately from this theorem, since in our case, M modulo tors M, all localizations are free. Okay, I think that's everything I am going to tell about this tilde category at the moment. So thank you very much. Thank you.
Thank you.
And
are there any questions?
Yes, I have a question. Yuriy Anatolyevich, what is the examples of these pseudo-Noetherian and pseudo-Krullian rings, which are not usual?
Actually, I was interested mainly in Noetherian reduced rings, but namely the main thing is that it is locally defined, that it is equals its intersection by localization at primes of height 1. This is the main thing.
Can I ask a question about the global dimension? So this is theorem 2 or 3. Is it true that the global dimension is either 2 or infinity?
You mean theorem 2?
Yes, theorem 2 about the global dimension. So my question is, it is either 2 or infinity. Is it kind of true?
What?
So my question is the global dimension is 2 or otherwise infinity? Infinite global dimension.
Yeah. You see, there are examples of Noetherian rings, even Noetherian rings of
Yeah, okay. And concerning the answer
yeah. You are quite right, yes. Because of this.
Okay. And concerning the question of Professor Ettinghoff, since the localization is semi-simple Artinian ring, this is precisely by Goldie theorem is a kind of semi-prime Goldie ring. So there are plenty of such objects. Yeah. Okay.
No, you mean what is it?
So as I you see, so when consider your ring, you consider the classical quotient ring, and this is precisely the semi-simple Artinian ring, right? Is it correct? Yes. So by the Goldie theorem, by the classical Goldie theorem, this is a precisely semi-prime left
But
Goldie rings.
we are talking about commutative rings, right?
No, these rings are semi-prime, yes.
And for commutative ring, it's true as well. So it doesn't matter.
Yeah.
Or non-commutative. It will be commutative semi-prime left Goldie rings. There are plenty of such a ring, and these rings are not necessarily commutative. But yeah. So this is answer to your question.
Yeah.
Okay.
Yes.
Okay. Thank you.